Hello and welcome everybody to this presentation. In this presentation we are going to look at Thevenin's theorem, which is a very useful theorem in electronics. And let's have a look what this Thevenin's theorem is useful for. Let's suppose we have a very complicated circuit. For example, we have a few voltage sources, resistors, more voltage sources, and so on. We have a very complicated circuit. For example, another voltage source here, and so on. And what we want to do is to replace this circuit with a much simpler circuit. What Thevenin's theorem say is that whatever linear circuits with voltage sources and resistors, these circuits can be replaced by a simpler circuit consisting of only one voltage source in series with a resistor. Like this. Maybe you have a load in here and so on. So if we have this circuit, then there's a way that we can transform this circuit into this circuit. So how is that possible? Well, there are two things that we need to do. The first thing is we have to select which points we want to analyze in the circuit. So let's say we are interested in the voltage from this point to this point here. The first thing you have to do is you have to remove all the voltage sources in the circuit and replace them by a normal just conductor, just wires. You pretend the voltage sources are not here, and then what you do is you measure the resistance from this point to this point. If you have a practical circuit, you can just take a multimeter and measure the resistance directly here, after of course shorting the voltage sources if you can. If not, then if you have a theoretical circuit like this, then you have to calculate the resistance. You have to remove the voltage sources and just calculate the resulting resistance from here by just simplifying parallel and series resistors and so on. So you find the resistance R, and this resistance R is going to be this resistance here. We call it R0, which is the source resistance. Now the second thing you need to do is you have to find the voltage from this point to this point, the open circuit voltage from this point to this point. And that simply means if you have a practical circuit, you just take the multimeter and measure the voltage from this point to this point, and whatever that voltage is, that is going to be this voltage here, and this is V0. Okay, so after that, then you will have the voltage, both the voltage and the resistance. And so you take that voltage and that resistance and you create an equivalent circuit like this that has that voltage that you measure and the resistance that you measured. So this is it. This is Thevenin's theorem, and it can simplify any circuits of this type, consisting of voltage sources, resistors, and also current sources. But we'll leave that to another video. Now let's do an example of this. Let's solve a circuit, and the circuit I'm going to choose is a very simple circuit, but a very useful circuit that we find everywhere. And this is just a pattern which is called the voltage divider pattern. So here we have a voltage source and we have resistors R1 and resistors R2, and we have this output here on the circuit. So we are interested in these 2 points here. So imagine, for example, if you were given these 2 points here and they were coming out of a black box, and you want to figure out what the circuit inside is equivalent to. So after doing what we did upwards, measuring the resistance here and measuring the voltage, then you can replace this circuit, whatever it is, with a simple circuit consisting of a voltage source and a series resistance. But let's suppose we have the circuit just here on the diagram, and it's a theoretical circuit. There is also current I flowing in here. Okay, so what can we do here? We need to find, first of all, let's find what is the voltage around from this point to this point, And as you know, this is a voltage divider, so the voltage from this point to this point is simply going to be given by R2 divided by R1 plus R2, which is the ratio of R2 to the total resistance on here, and then you multiply this by VI, which is this voltage here, and this is going to be equal to your voltage V0. Okay, so now after that, what you do is there are two options to go about here. The first one, now we're interested in measuring the resistance from this point to this point when the voltage here is shorted. So either you measure the resistance here with the voltage shorted, or you can measure the current of the short circuit here. If you short this side to this side and measure the current flowing in here, then you take that current and this V0, and the V0 divided by the current is going to give you the resistance. Let's go the more usual way, I suppose, and just calculate the let's find what is the resistance here. So to find the resistance, you short circuit the voltage source, and you look at the circuits that you have. So then when we short the voltage source, then our circuit is going to be this circuit here, and we have these outputs here. And so the resistance between this point and this point, if you look here, this is R1 and R2. R1 and R2 are in parallel in this circuit here. So the resistance from here, from this point to this point, is going to be the parallel resistance between R1 and R2. And if you remember the formula, we have for a parallel resistor is 1 over R is equal to 1 by R1 plus 1 by R2. So this implies that 1 over R is equal to R1 plus R2 divided by R1 times R2. And so the resistance is the inverse of this, so it's R1 R2 divided by R1 plus R2. So this is our resistance. So this is V0, and so R0 is equal to R1 times R2 divided by R1 plus R2. Okay, so therefore now we have the resistance and the voltage, and so we can reconstruct this circuit as a simple voltage here in series with a resistance here, and we take the output here, and now this resistance here again is R1 R2 divided by R1 plus R2, and this voltage here is VI times R2 divided by R1 plus R2. And this is therefore the Thevenin equivalent for the voltage divider circuit. And I thought I would make more examples, but I'm not sure. I think this is enough for now. And let me see. Yes, for example, let's do another example. Um, let's suppose, for example, that we have this circuit, the same circuit here. Let me copy it down here. So we have this circuit. Let me copy the formulas here. Paste. So let's suppose that we have this circuit, except that we have another resistor here. And let's suppose that we attach our resistor here, which is our load. And so we want to figure out what is the voltage on this across this load here. Notice that this voltage will not be equal to the voltage of the open circuit here, because whenever you attach a load into a voltage like this, into an open voltage, the voltage is going to decrease because you are now drawing current through the point. So the points will be at a lower voltage here. So if we have this circuit, then what is the voltage? Let's figure out what is the voltage and the current on this point. If you remember, you can The first thing you can do is you can figure out what is the parallel combination of these resistors without using these formulas. Figure out what is the parallel combination of these, and you're gonna have a single resistor here. From that you can calculate the current that is flowing on here and also the voltage, and that voltage here is going to be the same voltage as is flowing on this resistor. So let's do this. So when we have a resistor here, we can use the simple version of this circuit, and then we have the load here. And now let's remind ourselves that this resistance here is R1 times R2 divided by R1 plus R2, and this is VI R2 divided by R1 plus R2. So as you can see, by using this pattern, we have simplified the circuit considerably. Instead of having to calculate the parallel resistances and currents on here, which will require more calculations, we just use these patterns. So you just have to memorize these formulas here for the voltage divider. So now from here, you can figure out the voltage across RL, and this is simply RL. Oops. This is simply another voltage divider. It's RL times, so it's our RL over RL plus this resistance, which is R1 R2 divided by R1 plus R2, times this voltage, which is VI R2 divided by R1 plus R2. And so if you simplify this, this is equal to RL R2 times VI divided by, so you multiply this on both sides, so this is RL R1 plus RL R2 plus R1 times R2. And so this is the voltage on this resistor RL here, and this is going to be the same voltage as on here. And from this, of course, you can calculate the current. So the current I is equal to the voltage over the resistance RL, and so it's this divided by RL, so it's simply equal to R2 VI over this stuff here. Okay, so I hope you have enjoyed the video. So as you can see, it's very useful to know Thevenin's theorem, and very useful to know patterns for voltage dividers and the Thevenin equivalent for voltage dividers, because it can simplify your life a lot. So that's it for now, and until the next video, I bid you farewell.